In our systematic procedure to obtain the control structure, we have gone through item 1, the control objective and the choice of PV. Item 2, well, the list of all candidate MVs. Item 3, the list of all perturbations on the system, so output disturbances and input disturbance or load disturbances. And we have arrived at item 4, the list of all constraints, the list of all CVs. Well, constraints come in different forms. First of all, we have the constraints on the actuators, right? And we have absolute limits, MV min and MV max. In the example of a valve, well, MV min is of course 0% opening and MV max is 100% opening. But you also have limitations on the rate. Okay, so the speed of the opening of the valve. For instance, a valve might open at a maximum speed of 10% per minute, for example. There are of course also limitations on the set points of secondary controllers. For instance, in our Cascade temperature fuel flow control, well, the set point of the secondary controller is, well, the fuel flow set point, and there is of course a maximum value for this set point. Besides constraints that are on the actuators, so on the MVs, you have also constraints on the process values, so on the PVs. Again, you have, well, limitations in absolute values. A good example of that is the maximum level in a tank, but you can also have, again, rate limitations. It could be, for instance, that the boiler constructor specifies a maximum increase of the temperature in a given time period. Some constraints come in the form of relations, ratios between variables, and this is the case, for example, for a combustion. There is a relation between the fuel flow and the airflow, and this is to control the oxygen or air excess. In this representation of the preheating furnace, we have represented a damper. Usually there is more than one. A damper is a mechanical device that is used to regulate the airflow. Damper is registre in French. We can now have a look at all the constraints that are present in this preheating furnace. The first constraint is rather obvious. Well, it is related to the maximum opening of the fuel flow valve, here given in green. The next constraint is related to the maximum damper opening and the associated maximum airflow. As mentioned before, we need in this combustion here in the furnace to control the excess air and the excess oxygen, and this is done by, well, controlling the ratio air to fuel flow. And finally, there are constraints on the temperature inside the heater imposed by the constructor. So constraints on the maximum value, so the maximum temperature inside the heater, but also, well, constraints on the maximum rate of change, and this is at the startup of the line, right? So there is a maximum increase of the temperature in a given time period. The constraints on the damper and on the fuel flow valve might come into play if we try to maximize the product flow. So you can see here that there is now a valve that allows you to control the flow of products. So you have here a product flow set point, right? And this set point is set by, well, the downstream process, for instance, the distillation column that sets the demand of product flow. But you can see that if this product flow is increasing, well, this valve will start opening because you'll need more fuel flow, and of course because of the excess air relation, right, we also need to open the damper. So you can see here that if you continue to increase the set point, what will happen is that you run in the limitations associated to the fuel flow valve and the damper valve, and this is what you see over here, right? So we have to handle fuel flow and damper constraints. This will be explained later in the course. As mentioned before, for the combustion in the furnace, we'll have to handle also the air flow to fuel flow constraints. Let us now focus on cascade control. We have already seen one example in the preheating furnace. It was a cascade temperature control, fuel flow control. So in this case, the outer controller was a temperature controller, the inner controller was a fuel flow controller. The inner process is the relation from valve position to fuel flow, and the outer process is the relation from fuel flow to temperature. But this is how you can depict a cascade control in general. Here you can see the inner loop, right, with the inner process and the inner controller. Sometimes we replace inner by secondary or slave, and here you have the outer loop with the outer process and the outer controller. Sometimes we replace outer by primary or master. Notice that the process that is seen by the outer controller goes from, well, the outer MV, which is the inner set point, to the outer PV. So it is the inner loop, right, in series with the outer process. When should we use cascade control? Well, let us return to our process here that is composed of an outer process and an inner process, and let us assume that we use here a single loop controller. So the controller is then simply C, and it uses the control error SP minus PV, and it produces an MV that is, well, sent to the process. So we see here the process as simply P, right? Well, a first necessary condition to use a cascaded control is that we have access here to this signal PVI, right? And if we have access, well, one reason why we would use cascade control are load disturbances. If there are load disturbances, they will be seen first here at this inner PV and later in the outer PV. If you use a single loop controller as shown over here, well, we'll see the load disturbance much too late, right? So clearly, if there is load disturbance, you should use the cascaded solution. Another reason is that maybe the relation from MV to the inner PV is nonlinear, and often this is due to, for instance, nonlinear valve characteristics. Well, then using this inner loop here, then we have here an outer loop, right? Well, we'll have a linearizing effect, in the sense that this closed loop will look linear from here, right? So this outer controller will see a process, which is this closed loop followed by the outer loop that is linear, right? So these are the two main reasons to use cascade control. It is very important in a cascade to make sure that the inner loop is tuned much faster than the outer loop, and this is what is shown over here, right? The closed loop time constant of the outer loop must be larger than 3 to 5 times the closed loop time constant of the inner loop. So here 3 is really a minimum, right? And to explain this, I always like to use the analogy cascade control and delegation of work. Well, problems are to be expected if the supervisor brings a subordinate work for 3 days every day, right? In the same fashion, well, the primary controller needs to give the secondary controller the time to perform its task. And if you use this constraint, well, you make sure that at the time constant of the outer loop, right, the inner loop is at least at 95% of its steady state. Remember that for cascade control, the inner closed loop time constant must be such that 3 times this constant must be smaller than the outer closed loop time constant, right? Well, if the inner loop cannot be tuned so that this condition is satisfied, because maybe MV is limited, the inner MV is limited, what you'll have to do is slow down the outer loop, and this can be done by decreasing the outer controller gain. Okay, the easiest way to tune the cascade is to use the IMC PID tuning method that will be introduced in the next section. And in this tuning method, the desired closed loop time constant is used as a tuning parameter, and it makes it easy to check and to impose that this condition is indeed verified. You have to use cascade control with caution if there is noise, high frequency noise on the outer PV, and this is for instance the case in level 2 flow cascades. So let us consider such a case. So we have a tank over here. Let us consider an input flow to this tank, right? And here we have a level measurement, right? So what we have is a level 2 flow cascade. So we have a local flow controller, right? And then we have this level controller that will set the flow set point. Assume now that there is high frequency noise on the level. Well, if you do not take any precautions, you will have these high frequency fluctuations at the output of your controller, okay, sent to this local flow control, right? So you will have set points that will fluctuate with the high frequency content, and this flow controller might not be able to follow. So what you'll have to do is, of course, filter the level, right? And you can run the filter with a smaller cycle time than the level controller. Okay, once you have filtered the level, well, at the output of the controller you will no longer have this high frequency content sent here to the flow controller. Remember that the process that the outer controller sees is the inner loop followed by the outer process. Okay, so if you change the tuning in the inner loop, well, you change the process seen by the outer controller. So it makes sense to use an inner to outer approach for tuning. So you first have to tune the inner control loop, and when you're satisfied, you can tune the outer control loop. It's very important to see that if you're switching in the internal loop from manual to automatic mode and back, or from external to internal setpoint and back, you can expect problems if your implementation of the interlocks is not done properly. For instance, if you're in manual mode with the internal loop, well, the cascade is broken, so you have to lock the outer controller. Very similarly, if your inner loop is saturated, well, then the cascade is open, right? The outer controller does not have any influence anymore on the process. So again, you could have this problem of integral wind up in the outer controller. So this management, right, of the interlocks must be done in a proper way, and this is what we'll discuss next. Let us look at the interlock strategy. So what could happen is that the secondary controller, or the inner controller, or the slave controller, is in manual mode. This means that the operator is directly imposing the inner MV, right? And whatever is happening here at the output of the outer controller, it's not taken into account, right? And this value here, this inner MV, is not going to make sure, of course, that this outer PV is on set point, so there will be an error. Yeah, if you do nothing, what will happen is that this error will be integrating, and the output will either go to a very large or to a very negative value, depending on the sign of the error. In any case, if the inner controller is in manual mode, then the outer feedback loop is broken. Well, what could happen is that this inner controller is in internal mode, which means that the set point coming from the controller is no longer taken into account, right? Generally, this internal set point will not make sure that the outer PV is on set point, so again you'll have an error, and if you do not program your interlock strategy correctly, this error will be integrated to a large or very negative value, which is problematic when you switch back to external mode. So clearly, again, if this secondary controller is in internal mode, the outer loop is again broken. So what we'll need to do in those cases is to lock the primary controller to prevent wind up. So remember that a controller comes with two inputs, track on and track val. Track on here is a binary signal, so it's either 0 or 1. If it is 0, then this controller is simply operating in normal mode, right? So it's the PID algorithm that is active. But if track on, this binary signal, is going to 1, then the controller is locked, right? And if track on is 1, then the output of the controller is equal to track val. Okay, and what we'll have to do now is, well, set track on and choose a certain tracking value. Well, this is how the interlock strategy is implemented. Well, you simply have to detect that this inner controller is in internal or manual mode. So this OR signal will detect that this controller is either in internal or manual mode, and you can connect it to this binary track on signal of the outer controller. So when this controller goes to internal or manual mode, this one will be locked, and what will happen is that will prevent the output and the outer MV here to ramp up, to be integrated to a very large value or to a very negative value. What we still have to decide on is, well, this track value. Remember that the output of this outer controller is going to follow this signal, and what you can do is use the inner process value as a tracking value. You can see that when this controller is locked, the output, the outer MV here, will simply follow the inner PV and will impose a zero control error here in the inner controller, right? What will happen is that the outer MV is ready when, well, this one goes again to external automatic mode. If this one is going to external automatic mode, this one will no longer be locked, and the output of this controller will start from the last inner PV when it was locked, and it will start to correct to make sure that the outer PV goes to set point. Note that another possibility when this one is in internal mode is to use the internal set point here as a tracking value. If you use the internal set point as a tracking value, well, at the output you'll find the internal set point, and you'll have it also as a set point for the inner controller. The advantage of this strategy is that it will work in internal and manual mode. In internal mode, right, well, if this inner loop does a good job, well, the inner PV will be very close to the inner set point anyway. Note that here we have locked the outer controller when this one is in internal and in manual mode, but you should also lock the outer controller if this one is locked. Okay, assume for instance that we have this flag here for this measurement that is indicating that there's something wrong with this PV, inner PV. What we'll do is lock this controller, but if this controller is locked, the inner controller, well, again, the feedback loop is broken, and you should also lock the outer controller. Interlock problems due to a badly managed and implemented interlock strategy is the biggest source of problems in real-life situations. This is why vendors propose solutions to mitigate these problems. Some vendors propose a function block, an FB, implementing the master and slave controller with a correctly implemented interlock strategy. So you have one FB implementing the whole cascade. Other vendors, and this is for instance the case in the Siemens PCS7 system, propose typicals, so CFC plans where the cascade is pre-programmed with a correct interlock strategy. The only thing that you have to do is then connect the input and output signals. The example of the jacketed chemical reactor is given for your information. It might be interesting for you to have a look at the next slides without going too much in the details. You will see that different cascaded solutions are investigated, and the solution that will have to be taken will depend on the load disturbances that affect the system. So let us come back to this cascade control that we have considered already before, when we had considered, well, different cycle times. Here the outer process has a time constant of 50 seconds and the inner process has a time constant of 5 seconds. So you can see that this inner time constant is much lower than the outer time constant. You can see here that the cascade is functioning properly. The inner loop here is in automatic mode and we are in external mode. So this means that this inner loop receives its set point from the outer loop. You can see here in orange the outer MV and here in blue the inner set point, and they correspond all the time, right? This one is simply in automatic mode. So what you can have a look at is the tuning. We haven't talked about tuning so far, but you will see that here we have an integral time constant of 4 and a gain of 1, right? And here we have a smaller gain and an integral time constant of 40 seconds. So this inner loop has been tuned to be much faster. What we can now do is have a look at a set point response and go, for instance, to 170 degrees Celsius. You can see here in blue, dark blue, this is the set point of the outer loop, right? And you can see the set point of the inner loop, which is really the MV of the outer loop over here, right? Here, this curve over here is the inner PV, right? And you can see here in light green, this is all indicated over here. So the outer controller is a temperature controller and the inner controller is a flow controller. And this is the response that we obtain after a while. Of course, we are interested in the programming of the cascaded solution, and what I've done here is look in the libraries and look in the templates, and you can see here indeed that you have a pre-programmed cascade control structure, and this is the one that you see over here with a master controller and a slave controller, and the only thing that you have to do is to connect here the inputs and outputs. They are given here in green. Well, let us now have a look at the interlock strategy that has been pre-programmed. So we can have a look at the PID master, and you see here that you have MV track on, MV track, so the names are a bit different, right? But if we click on this signal, we can go and have a look where it's coming from, and it is the PV from the slave controller. So this is okay, it is as expected, and we can also have a look at the MV track on. So this is the binary signal. Well, it's an OR. If there's a problem with the PV from the master controller, then this binary signal will go to 1, which is kind of nice, and it's also coming from this output, and this one is coming from the slave controller. And here there is an output of this slave control that is called cascade connection cut, right? So for instance, when this controller is going to manual mode or to internal set point, this one will go to 1. So as you can see, this interlock strategy has been correctly programmed in this template. So what we can now do is go online and look at the actual online values, you can see that this block is not, this is the master PID, is not locked for the moment. And if we look at the slave, right, we can see that the cascade is not cut and it's actually in automatic mode with an external set point, as you can see. What you can now do is go to the WinCC interface and take this one to, for instance, manual mode. As you can see over here, there is a T for tracking, so this controller is now locked. As you can see, the master PID is locked, so MV track on, this binary signal is 1, and the output MV, as you can see over here, is tracking MV track. So if we have a look over here, we see indeed here that this slave controller has an output cascade cut that is now 1, and this is why the master PID is locked. Well, we can see that if we put it back in automatic, then this one is no longer in locked, but that if we set it to internal mode, you will have the same thing, so this controller will also be locked. So let us go back to external but manual mode, and let us change the manual value to, for instance, 10%, right? Of course the fuel flow will decrease, right? And as you can see, of course, the temperature will drop, but there is no wind up at the output of the controller, so this one is in tracking mode, it is locked. So the output here is simply following the PV of the internal loop. It's time to do a little quiz, and the quiz is about cascade control and interlocks, right? So here in the top plot, what you see are the SPs and PVs associated to this cascade. In the dark colors, you always see the curves associated to the outer loop. So for instance, in dark brown, the outer set point, and in dark green, the outer PV. And you have something similar for the MVs. So in dark blue, the outer MV, and in light blue, the inner MV, right? So you have to look for the correct answer among those 5 candidates. So you have to associate the response with the correct diagnosis. What you can do is use the pause button and the rewind and forward functionalities to find the correct diagnosis. Let us see if we can set the correct diagnosis. We see here in these 5 possibilities that the inner controller either goes to manual mode or to internal set point mode or into saturation. Let us look at the internal MV here and see if this controller goes to manual mode. You can see over here that, well, MV continues to evolve, so it does never go to manual mode, and you cannot see any saturation of MV. This means that you can already exclude the answers A, C, and D. Well, let us see if this inner controller is going to internal set point. The internal set point is given in light blue, and you can see that indeed here this controller goes to internal set point. So here it's receiving its set point from the external controller, and then it goes to internal set point, to a fixed internal set point of, well, 5 here. So if the interlock strategy is implemented correctly, the outer MV in dark blue should be following the inner PV, right? And this is clearly not the case, and you can see that because of the wrong implementation of the interlocks, the MV is increasing, it's being integrated, so there is integrator wind up. So clearly the correct answer is when the inner controller goes to internal mode, the interlock strategy is not implemented correctly, so it's answer E. So here's a second quiz, again with Cascade control and interlocks, and the color code for the measurements is exactly the same. And well, the same 5 alternatives are used, but they are not in the same order. Again, we can see that this inner controller is not going into manual mode and it is not saturated. So clearly we have to have here an inner controller that goes to internal set point mode. This is indeed the case. You can see it over here. And in this case, we can see that the interlock strategy is implemented correctly because, well, the outer MV here in dark blue follows the inner PV, right? So there is no wind up of the outer MV, and this is why when everything goes back to normal, so when the inner controller goes back to external mode, well, there is no dewinding of this outer MV, and the outer PV will go to set point much faster than in the other situation. So clearly the correct answer is this time when the inner controller goes to internal set point mode, the interlock strategy is implemented correctly, so answer E. In this subsection we'll concentrate on feed forward, and the idea behind feed forward is to eliminate the effect of disturbances before they create a control error. So we want to ensure control performance by anticipation of the disturbances, and for that we need upstream information. So we need a measurement which detects the influence of the disturbance sufficiently well in advance of the process value PV. Let us now compare feed forward and feedback and start with feedback. Feedback comes with a number of advantages. It is versatile and robust, which means that the feedback principle will work to reject any source of disturbance and any type of disturbance, whether it is a load disturbance or an output disturbance. Of course, as long as the disturbance is within the bandwidth of the closed loop system. If you use a PID type controller, then little knowledge of the process is needed, right? But of course it might help when you're tuning the PID controller. Of course, if you're using a model-based controller, as investigated later in the course, then of course a process model is necessary. Feedback control is slower and is subject to stability problems if you're careless. You need a control error to detect the disturbance, and by definition, a perfect rejection of the disturbance is not possible using feedback only. This is what we mean by perfect control is not achievable. For frequent and severe disturbances, the process value might not even settle out. The advantage of feed forward is that the corrective action is taken before the process is upset, so before you see the influence of the disturbance on PV. And in theory, perfect control is possible, is achievable. Unless you're really careless, right? Feed forward should not affect the system stability. Feedforward comes with an operational cost in the sense that you need an extra sensor to detect the disturbance. A good model of the process is required to implement feedforward. And indeed, we need a model of the process, and we need also a model of the disturbance dynamics to implement the feedforward action. We will see later that the feedforward action can be implemented as follows. So it is the dynamics of the disturbance then times the inverse of the dynamics of the process, and it's acting on the disturbance variable. In practice, you have to use models of the input-output dynamics, P, right, and a model of the disturbance dynamics, D. In the background, what will happen, because you have to go through the process, is that you have an inversion of the process dynamics. So you have this one coming from the actual process, and this one is coming from the feedforward, as you can see over here, but those two will cancel out, and therefore this feedforward action is not robust, because variations in the process will have a major impact on the feedforward law, since this one is going to remain fixed, right? If this one is fixed and this one varies, well, we have a major impact on the feedforward, in the sense that the variation of P is entirely reflected on the feedforward law. This feedforward here is an ideal feedforward. It will result in perfect control, but in practice it is not always physically implementable. And this is the reason why feedforward and feedback are combined. In practice, you will never or almost never see feedforward used alone. The feedforward then is used to eliminate the effect of the measurable disturbances before they have an effect on the process value PV, and the feedback will ensure tracking performance, static error that is 0 in steady state. It will correct for those disturbances that are not measurable, right? And it will ensure robustness in the presence of process variations. The first principle of feedforward is to implement a static feedforward. The idea is very simple. It consists in pre-computing, between quotes, the MV that you need to make sure that the process value PV is equal to the set point given the disturbance dV, or given the disturbances dV. This will often be done using an energy or mass balance. Instead of mass balance, you will find the name material balance. The feedforward will require, of course, the dVs, right, the disturbances, and the desired set point. We had already seen an application of this type of feedforward for the preheating furnace. The feedforward, shown in green here, is based on an energy balance, and we had been able to pre-compute the required fuel flow to bring a product flow FP from an input temperature Ti to a desired output temperature T set point. Well, let us take another example of this type of feedforward coming from the paper industry, and the paper process has been discussed in the introduction. The stock with a certain consistency is pumped to the headbox. This is the headbox, and we have access to the stock flow in liters per minute and to the consistency of the stock in percent. At the output of the headbox, a paper web of width W expressed in meters is produced with a speed expressed in meters per minute. At the end of the process, the paper is winded up on a reel, and there is a desired absolutely dry grammage set point expressed in grams per square meter. To give you an idea, the paper you're typically writing on has a grammage of around 80 grams per square meter. More details about this paper process can be found in the introduction. You will see that the process engineers and the operators are capable within seconds to compute the stock flow that is needed to produce a paper with a certain grammage. What they do is use a mass balance, and we can use the ID for feed forward. It is actually rather easy to compute how many kilos of fiber per minute you have to put on the wire at the beginning of the machine. You just take the grammage that you want to produce, right, and you go through this formula over here. So what we see is that we go from grams per square meter to kilos per square meter, right, by dividing by 1000, and then we multiply by the width of the paper web and the speed, and we obtain the desired quantity of fibers expressed in kilos per minute. Of course, this is neglecting, for example, well, the trim. You might have seen in the video that a little piece of paper here is trimmed, and you have something similar on the other side. So this is of course not taken into account in the mass balance, but this is not a problem because this is going to be taken care of by the feedback. Well, here we know how many kilos of fibers we have to put on the wire per minute, but of course we have to translate this, right, to a stock flow expressed in liters per minute. And without going too much into the details, but what you have then to do is to take the consistency into account to produce the stock flow. You can kind of see that if the consistency of the stock is low, well, you will have to have more stock to make sure that you reach this amount here expressed in kilos per minute. So as you can see here, this is really a feed forward, right? You use the measurement of the speed and the consistency to kind of pre-compute the stock flow. And if there are variations in the speed and the consistency, you can use this feed forward to kind of make sure that these disturbances are rejecting by reacting immediately, right, and not wait until you see the effects on the actual grammage. Once the stock flow has been pre-computed, you can use it as a set point for a local stock flow controller. So you can use a controller here to make sure that this stock flow set point is followed by the actual PV. You will see that this will later be associated to a grammage controller, so you'll have a cascade structure grammage stock flow with associated feed forward, and the advantage is that, well, load disturbances in the form of pressure disturbance here at the input will be rejected using this local stock flow loop. Well, we have seen before that feed forward should not be used alone, right? So the control scheme is incomplete. This width that is used over here is probably not the exact value. This is here a measurement, so there is no measurement that is exact, and this is even more the case for this consistency measurement that is considered to be rather imprecise. So this is going to help you right? Ensure that this grammage set point is met, but what we need is a feedback mechanism, and this is what you see here on the screen. The grammage feedback controller is not a PID controller, but is often a model-based controller with scheduling of the model parameters. This will be discussed later on in the course, and as you can see, the controller corrects the mass flow that has been pre-computed by the feedforward. By correcting the mass flow in kilos per minute and not the stock flow in liters per minute, we can use the consistency measurement to anticipate the influence of consistency variations on the total mass flow. In the control scheme that we have obtained so far, we see that a grammage set point change in the form of a step is going to be taken into account twice, once by the feed-forward mechanism and a second time by the feedback mechanism, right? Because if there is a set point change over here, what will happen is that there will be a kick here, something that will look like this, at the output of the controller. So we have to prevent this kick when we have a set point change at the output of this feedback controller. Well, there are several ways to prevent this kick here at the output of the controller that would take into account the grammage set point twice, once using feed forward and once using feedback. The first one is to use a filter or a transfer function that can be used to mimic the expected closed loop response of the system, right? Then the controller will only react to, well, deviations with respect to this desired closed loop response, and you will not have this kick at the output. This is one way. Second way is that you could use a ramp on the set point and make sure that this controller, and it's only this controller of course, will sees a ramped set point, and it would then look like this. Okay, and this is also a way to prevent this kick here at the output. And a third methodology, and this can be used if you're using a PID controller that has this functionality, and we'll see this in the next section on the PID controller. Well, it's use a controller that uses a proportional error, that is B set point minus PV, right? And you put this one to 0. You see that the influence of the set point is taken out of the proportional error. Of course, the set point is still present in the integral action, but not in the proportional part, and this will also prevent this kick at the output. As I said, this will be viewed in the next section. Well, this danger of acting twice on a set point change, a step-like set point change, also exists in this example, because the set point, well, is intervening in the feed forward but also in the feedback. So again, we have to prevent that this set point change on the temperature is taken into account twice. So the three tricks that have been given on the previous slide are also applicable here. The second methodology or principle leads to a dynamic feed forward, so it requires the knowledge of the process dynamics, we'll call it P of S here, from MV to PV, but also the knowledge of the disturbance dynamics from DV to PV, and this can be obtained through experimentation. Although this is easier for the process dynamics because you can influence MV, right? For instance, if you have a controller in front, put it in manual and put a step at the input over here and look at PV. This is of course more difficult for DV because very often you cannot influence DV and you have to live with the DV that is present on the process, right? And you have to collect a data set with DV and PV. Then you have to use some kind of data driven modeling package to obtain this model of the disturbance dynamics D of S. What you could do is use IDs similar to what you have done in the laboratory associated to fundamentals of control theory and use, for instance, the function fmean search in MATLAB to obtain this model. Well, the ideas behind this second methodology leading to a dynamic feedforward are very easy. Well, you have a first influence path of dV on PV, and it's really, well, dV going through the disturbance dynamic. So you can write it like this: D of S acting on dV, right? And the idea is to, well, create a second influence path that will go through the process, right? And that will compensate this one, right? So if you go through the process, of course, in this second influence path, we have to cancel the process dynamics. So this is why in the feed forward you have the inverse of the process dynamics. This one will cancel out with this one, right? And of course then you need to give it to shape this second path so that it has exactly the same dynamics as the first one, and of course you need to give it the correct sign. Okay, so you can kind of see here that if you have an exact model of the process and an exact model of the disturbance, what you will see over here is minus D of S dV, right? D of S acting on dV. In practice, what you will have over here will be, well, not this, but I'll write it in another color to just show you that this is what happens in reality. Well, it's not D of S, but it's a model of D of S over the model of your input output process dynamics times P of S, and the whole thing acting on dV, right? And if your models of the disturbance dynamics and the process dynamics are sufficiently good, well, this is going to give you a good compensation, a good rejection of this disturbance dV. Well, as with the first method, feedforward is not going to act alone, so it's always working with a feedback. So this one is coming from a feedback controller. So you have to imagine here a controller PV that comes in the set point, and this one is generating this correction on the feed forward action, right? And the feed forward action, in words, it's the disturbance dynamics over the process dynamics with the correct sign minus here, so that you have this second influence path that in theory will perfectly compensate the first influence path. Well, we have seen that the manipulated value is constructed from the feedback part coming from the controller and the feed forward part, right? We put the minus sign over here, and therefore we can write it like this. It's the dynamics of the disturbance divided by the dynamics of the process acting on dV, right? And now we'll have a look at this ratio here, dynamics of the disturbance divided by the dynamics of the process. So now we need quantitative information about this D of S and P of S, and what we'll do here is say, well, this dynamics is a Broida model. Gain, time constants, delay, and same thing for the process dynamics. Of course, the same IDs apply if we are using higher order models. For instance, a Van der Grinten model, 2 time constants, a delay and a constant, right? Of course, we have to make sure that this one is realizable, but this will be discussed later, right? Well, if we write this D of S divided by P of S in this particular case, what we'll have here is, well, KD divided by KP, so this will be the feed-forward gain, right? If we divide this one by this one, what we'll have is TPS plus 1 over TDS plus 1, and this is a lead lag system, right? And for this one we have to pay attention. It's exponential of minus theta ds divided by this one, so we'll have the exponential of theta ps. This one you can rewrite as the exponential of minus theta d minus theta p s, but a delay should be larger than 0. So what we'll do is rewrite this differently. We'll rewrite it as exponential of minus theta feed forward s, right? And this theta feed forward will be theta d minus theta p as long as it is positive. So how can we write this? Well, we can say that theta feed forward is the maximum of 0 and theta d minus theta p, right? If this one is negative, right, well, 0 will be selected. And this is really the feed forward dynamics if we have dynamics of the disturbance and the process that are Broida models. But as I've said, the same IDs apply if you have higher order models. You simply have to divide D of S by P of S. And indeed, this is the dynamic feed forward that we obtain. Assume here that both the disturbance dynamics and the process dynamics are described using this Broida model. And this is how it looks like in the form of a control scheme. And again, this is what you obtain when both the disturbance dynamics and the process dynamics are described by a Broida model. Well, let us use this to look a little bit at the intuition. For instance, if theta d is equal to 10 seconds and we have here a delay in the process of 5 seconds, well, it makes sense then to make sure that we have a feed forward delay that is 5 seconds, right? It will be theta d minus theta p is 5 seconds. It's positive, so we keep the value. But you can see that in this second influence path, if you add the two, you also have a delay of 10 seconds, so that you adjust when those two influence paths act and that they are acting at exactly the same time instant. Well, let us now take an example where we have a delay in the disturbance dynamics that is 5 seconds, right, and a delay in the process that is 10 seconds, right? Well, theta d minus theta p is minus 5, but we cannot use a negative delay, so we have to use here theta feed forward is equal to 0 seconds, and therefore you cannot adjust the first influence part and the second influence part. So if, well, theta P is higher than theta D, the delay in the process is higher than the delay in the disturbance dynamics, then we have to accept imperfect compensation. Well, let us now have a look at the time constants Td and Tp and assume that Td is smaller than Tp, so the dynamics here are faster than the dynamics of the process. Then we would expect the feed forward to give a kick in the butt here to accelerate things, and this is indeed what is going to happen, right? If Td is smaller than Tp, if we only look at this part and we look at the step response of this lead lag system, it will look like this, right? Because the high frequency gain, and this is what you see over here, is larger than 1, right? So we'll have a kick and then it will go to 1, right? If this comes as a surprise, this means that you have to go back to the subsection on the lead lag system in the previous section. But anyway, this is consistent with what we expect. Let us take the other situation where the time constant of the process is smaller than the time constant of the disturbance dynamics. So this means that this dynamics is faster than the disturbance dynamics. So you expect kind of the feed forward to say, hold your horses, do not go too fast. And indeed, if you look at the lead lag behavior, you will see that this is indeed the case, right? So again, we can have a look at the step response of this part of the feed forward, and the response will now look like this, right? And as this one is smaller than this one, at the origin we'll have this direct feed through term causing something that is now smaller than 1, and the response of this part will look like this. We have already seen that the ideal feed forward is not always realizable. In order for the feed forward to be realizable, this relation must hold, but if the delay of the process is higher than the delay in the disturbance dynamics, well, this ideal feed forward is not implementable. In order for the ideal feed forward to be realizable, the resulting feed forward equation must be proper. This means that the degree of the numerator is less or equal than the degree of the denominator. Let us take an example. Assume that we have a second order system, and this is really the input-output transfer function. So we have 2 poles, and assume that the disturbance dynamics is described by this transfer function Kd over TdS plus 1, right? If we have a look at D over P, what we'll have is Kd over Kp, and then we'll have, well, these ones at the numerator, Tp1 S plus 1, Tp2 S plus 1 over TdS plus 1. So you can see that, well, this transfer function is not proper, so the ideal feed forward is not realizable. So 2 things that you can do: you can forget about this lead here and just implement this lead lag, or you add a lag and you use, for instance, alpha Tp2S plus 1, and then you have 2 lead lag systems, right? But this is clearly an approximation of the ideal feed forward. And alpha, for instance, is, well, well, in between 0.1 and 0.5, let's say, right? And this will make sure that the feed forward is now proper, but it is only, as I said, an approximation of the ideal feed forward, which is itself is not realizable. Remember that unstable poles or zeros cannot be cancelled, as this would go against internal stability, as we have seen before. So we have to make sure that this does not happen, and this might be another reason why the ideal feed forward might not be realizable. Let us take an example. So the input-output dynamics is in this case described by this, well, second order lead lag. So we have the lead here, S+1, and we'll assume here that the lead is negative. So we have here a system with a inverse response, right? We have two time constants, let's say. So TP1 over here and TP2 S+1, right? And the disturbance dynamics is simply a first order dynamic, so TDS plus 1. So if we look at D over P, what we'll have here is KD over KP, right? As usual, we'll have these two at the numerator, TP1S plus 1, and then TP2S plus 1. We'll have this one here at the denominator, and we'll have the lead here at the denominator now. And well, this is the feed forward, but this feed forward, okay, is going to go through the process, and it will cancel, right, the lead that you have at the numerator, but this one is negative. So here we have an unstable, between quotes, pole zero cancellation, right? And this is not possible. This means that you cannot, in this case, cancel the unstable, between quotes, zero of the process. Well, we have seen that dynamic feed forward involves the use of one or several lead lag systems. We have also seen that when the delay in the process is larger than that in the disturbance dynamics, then perfect compensation is not possible, simply because here you would have something that is negative and the delay is always positive, of course. But if you remember the Taylor series of the exponential, and you know that it's approximately 1 plus x, well, you can kind of approximate a delay, right, by a lead time constant, and that you can rewrite like this. So if the delay in the process is larger than the delay in the dynamics, perfect compensation is not possible. But what you can do in your feed forward, if this is possible, is to add an extra lead in your feed forward law, and this one will have then a time constant that is positive, right? It is also very important to beware of large lead constants. In our case that we have tackled, where the two processes were Broida models, we had a lead lag TPS plus 1 and TDS plus 1, and the high frequency gain of this lead lag here is TP over TD. If this is too large, well, this might amplify the noise that is present in DV. So you have to kind of then accept imperfect compensation, because otherwise the DV is amplified too much. If the lead is small, if means that the process time constant is much smaller than the time constant of the disturbance dynamics, right? Well, then the lead is very small. Then what you can do is simply approximate this by just a lag time constant 1 over TDS plus 1. Well, in order to check if the dynamic feed forward is working properly, what you should do is of course test it in the presence of a disturbance, and of course you should make sure that your feedback controller is in manual mode, so that the controller does not interfere with this monitoring of the dynamic feed forward. If it is in automatic mode, well, obviously the controller will interfere and try to make sure that PV is going to set point, and you will not be able to discriminate between what comes from the feedback and what comes from the feed forward. So when you're checking your dynamic feed forward, put the feedback controller in manual mode, right? So here we have a step-like disturbance, right? And we look at the influence on PV, and we can kind of see that after a while there is a lasting deviation between PV and the set point. This means that, well, the gains in the two influence paths, the one that comes from the process, right, that goes through the disturbance dynamics, and the one that goes through the feed forward, right, are not adjusted properly. So if you see a lasting error, a lasting deviation from a set point in the presence of a disturbance, with of course the manual mode, and assuming that you've started of course with a PV on set point, this means that the gain in the feed forward has not been chosen properly. We'll again look at a step-like disturbance on DV. Again, we assume that the controller is in manual mode and that PV is on set point before we see this step-like disturbance. And we have here the response on PV. PV goes back to set point, which means that, well, the feed forward gain has been chosen properly. But you can see here this sharp edge on PV, and this is indicative that the delays in the two influence paths do not match, right? And this is an indication of a wrong delay in the feed forward. Again, we look at a step-like disturbance, right? And the controller is in manual mode with PV on set point. This time, well, we have a much smoother response on PV. We see that there is a control deviation, but that it goes to 0. So we can conclude here that the gain in the feed forward has been chosen properly. Since there is no sharp edge, well, that the delays have been chosen properly as well, but that there must be something wrong with the dynamics in the lead lag, and this is an indication of a wrong choice of time constants. Okay, of course in reality you will not either have a wrong gain or a wrong delay or wrong time constants, but this will help you to kind of improve on your dynamic feed forward by looking at this type of curves, right? This all presupposes also that you can influence DV as you like, which is of course not always the case. As you can see, I will skip some slides that are there for your information only. These slides are an additional set of comments. It is also shown that when the dynamics of the process and the dynamics of the disturbance are similar, then the feed forward becomes static again, and finally set point feed forward is also investigated. So have a look if you're interested. Well, let us do a little quiz, and the quiz is about feed forward, and the question is the ideal feed forward realizable for the system that is given. And what you're given is each time the disturbance dynamics and the input output dynamics. So by ideal feed forward we mean the one that is capable of a theoretical perfect feed forward, right? And simply it's true or false. We'll go over the 5 questions, and then what you should use is again use the pause button, the rewind and forward buttons to kind of answer the questions. Try to do this by yourself, of course. Well, let us have a look at the first system, right? Remember that the 3 possibilities to make the ideal feed forward not realizable is first properness, second problems with the delays. Remember that the delay in the disturbance dynamics must be larger than the delay in the process dynamics, and then you can also have unstable pole zero cancellations. If we look at this example, indeed we cannot have any problems with properness. If you take d over p, you'll have a proper feed forward. The delay in the process is smaller than the delay in the disturbance dynamics, and well, unstable pole zero cancellations are coming from a cancellation of the process, right? But here we see that in the process all the time constants, the lead time constants and the 2 lag constants are positive, so all the poles are stable and the 0 is stable between quotes, so you cannot cancel anything that is unstable, so you cannot have unstable pole zero cancellations, right? So in this case the ideal feed forward is indeed realizable. Well, let us have a look at the second system. Well, here clearly if we do d over p we have a problem with the properness of the ideal feed forward, so the ideal feed forward cannot be realized in practice. Well, in this third example we have a problem with the delays, right? The delay in the process is larger than the delay in the disturbance dynamics, so in this case the ideal feed forward cannot be implemented. It is not realizable. In this fourth example here we have a negative lead time constant, so here we have between quotes an unstable 0. This process has an inverse response. If we construct the feed forward, it will be d over p, but the feed forward will go through the process. What we'll do is cancel this between quotes unstable 0, and this goes against internal stability, so the ideal feed forward cannot be implemented, it cannot be realized. Well, let us have a look at the last system. We cannot have any problems with properness. If we look at d over p, the delay in the process is smaller than that in the disturbance dynamics, and here all the poles are stable and the zeros between quotes are also stable, right? They are to the left of the j omega axis, so you cannot have any unstable pole zero cancellations, so here the ideal feed forward is realizable. Well, it is also possible to implement this preheater example, this preheating furnace example in PCS7. So what has been done here is to implement a model of the preheater and then implement the control structure. You can kind of recognize over here the cascade temperature fuel flow, and here the feed forward that is acting on the product flow and the temperature at the input. So what we'll look at is at the response, for instance, if the product flow increases with and without feed forward. But before we do that, let's have a look at how this model is implemented and how the feed forward is implemented in practice. Again, we see here that in this Cascade, well, the secondary controller is in automatic external mode. Well, let us have a look at the emulation of the closed loop system. So this is really the process that is simulated, the preheating furnace, together with the controller structure. You'll find the process emulation over here, and as you can see, I have programmed an FB that emulates the dynamics of the preheating furnace. This has been done using some SCL code, okay, that implements the dynamics, and the IDs are very similar to what we have done previously when we have implemented a first order dynamics in, well, an FB, except here that the dynamics are a bit more complicated. Let us now have a look at the implementation of the control structure. What you see over here is the master controller. So this is the temperature controller, and this is the slave controller. So this is the fuel flow controller. This Cascade is very similar to what we have looked at previously when we had considered Cascade control. And what you have over here is the feed forward. We'll come back to that later. And here you have a PID controller that allows you to control the product flow. If we look at the feed forward, well, I've written here a block, an FB, that implements this feed forward. It takes the temperature set point at the output, and you have measurements of the input temperature and the product flow, right? And you can set the different parameters to compute this, well, feed forward gain based on the product density, the product specific heat, the fuel density, and the fuel heating value. And this is calculating the feed forward, the pre-computation of what you should use as a fuel flow, right? And you can enable and disable the feed forward. We can have a quick glance at the source, and you can see that this implements this feed forward that we had obtained in the slide. There is a slight change here, is that we can take into account the losses, right? In our energy balance, we had not taken into account the losses, but you can take it into account using this parameter K loss. Let us have a look to what is happening with this feed forward. Okay, this pre-computation of what you should use as a fuel flow. As you can see, it is going to the master PID to some input feed forward, and here is this PID master controller. So it is really the temperature controller, and this signal, right, is going into an input feed forward. We had called it MV underscore feed forward, but as you can see, the name can change. The idea is that what is coming from the feed forward and what is coming from the PID control algorithm, well, this is added inside the PID controller, and this sum is limited, is saturated between MV min and MV max. And in this case, well, it's not MV min that is used or MV max, right? But you clearly also have these parameters that allow you to limit MV between two values. Well, what we'll do now is look at a change of product flow and look at the impact on the output temperature and the temperature at the output of the preheating furnace, and we'll do this with the feed forward and without the feed forward, right? So we'll start with the feed forward enabled, as you can see. So let us change the set point to 1,000 liters per minute. So now the flow of product to be preheated is going to increase, and we're going to have a look at the output temperature. And here the set point temperature is given in blue and the output temperature is given in green, right? And as you can see, well, the product flow has changed here to 1,000 liters per minute. There is some impact on the temperature, but it looks rather small. What I'll do now is stop the simulation and come back to you when we are in steady state. So we have clearly arrived at steady state, and with this feed forward activated, we can see that the impact on the temperature is rather small. So what you can do is have a look and zoom, right? And you can see that the impact is less than half of a degree. Well, here we have returned to the original situation with a product flow of 800 liters per minute, and we're now going to do the test without feed forward. But before we do that, you can see here that the feed forward is asking for 5.6 liters per minute of fuel, and there is a correction by the controller. Okay, so the controller subtracts more or less 1.1 liter per minute, and this is because here in our feed forward we have used this K loss factor, well, not to have the ideal feed forward and have a realistic situation where you do not actually know perfectly the losses that you have in the system. And in this case, you can see that the controller will correct on the feed forward by adjusting everything in order to have the correct output temperature. Well, you can now do the same test, but with a disabling of the feed forward. To do this, we'll first put this temperature controller in manual mode, then switch off the feed forward, right? And now we can go to automatic mode, put this one on exactly 60 again. So the cascade is active without the feed forward, and what we can do is increase the set point of product flow to 1,000 liters per minute, as we have done before, and we will see what happens without feed forward. So as you can see here, the fuel flow has already reached the 1,000 liters per minute, but now it is the controller that must do the job without the help of the feed forward, and you can clearly see that the deviation is larger than without the feed forward. I'll come back to you later when it's in steady state. So we have clearly arrived at steady state. Let us have a look and zoom on the control deviation. And as you can see, well, the maximum control deviation is, well, more or less 3 times larger than what we had with the feed forward, and also the deviation is taking a longer time to go to 0, and this is because, of course, the controller has to act alone without the help of the feed forward. If we look at the curves and the responses with the feed forward again, you can clearly see here in orange that the output of the controller is clearly following the product flow increase, right? In this feed forward, we have used this K loss and we have used it too small. So what the feed forward has done is ask for a increase in fuel flow that is a bit too large, and you can see that the controller has to correct for that. We have done this in this simulation because if you use an exact feed forward, of course you would have the green line hidden below the blue line, and in reality your feed forward is never perfect. It's assisting your feedback for most of the job, but the controller has still to assist, and this is also the case in this simulation over here. If we are now looking at the curves without the feed forward, you can see that the output of the controller, here again shown in orange, is not reacting immediately on the increase of product flow. This is because there is no feed forward. This controller is reacting on the fact that the temperature is dropping. So this is because this controller is a purely reactive controller, and this is also why this deviation from the set point is of course larger.